So we were talking about those limiting distributions, and hopefully you saw that as the number of data points gets really large, then we can get sort of a limiting distribution, where what I mean by this is if n is not large, you might get sort of a histogram that looks something like this, but then as n becomes really large, then suddenly your histogram just gets really sort of dialed in with the bins, and you might start to realize a pattern in here. And I showed you a case of maybe a normal distribution, but it's like you need to get n getting kind of large before you can see that. So there's just a couple of relationships that I just wanted to show you here in analogy with sort of a finite number of numbers and sort of what happens when you get into this limiting distribution bit here. And so just a couple things. Remember that we can always have n number of data points, and each data point would be x sub I. And as we discussed, n sub I is sort of that important occurrence number. And then we even have this thing called the fractional occurrence here, which is sort of n sub I divided by n, which allows you maybe to even talk about percentages and that kind of thing. And so what happens to all these things in the limiting case of going to a limiting distribution? Well, the average, for example, here becomes, as we said, something like the occurrence times the data point divided by n, that kind of thing. And so what this would become then, as we recast earlier, it can be something like the sum of that occurrence fraction times the data point itself. But remember, this sort of thing is always for discrete data. But what happens with this data here is n gets really large, then the distribution doesn't come discrete anymore, but becomes continuous. Because you have so many data points, there's no gaps in anymore, and every feature could possibly smoothen over, and any data point that was going to merge was certainly be allowed to emerge. So instead of getting, again, a histogram that looks maybe something like this, you know, where this might be the frequency of occurrence and then the data point number down here, you can start talking about the actual mathematical distribution that you might get. So a couple things start to change. In particular, there's will be a mathematical function now, f of x, and on the x-axis here, that's sort of your x-axis right here. So what you can start to do then is say, okay, well, if it's a continuous distribution, then if this is some data that I'm interested in x right here, and down here on this lower axis here, I sort of have a width going here, which I might frame as dx, you know, some width in there, then I get a little bit of a rectangle in here. And you remember from calculus then that you can start forming the areas of these rectangles. And in fact, the term f of x times dx, that is this area. And so strictly speaking, this would be interpreted as sort of the probability of getting x between x and x plus dx. That's sort of what this would become then for the continuous distribution. Okay, the probability of getting x between x and x plus dx, and this would be sort of the continual analog of that frequency of occurrence fraction, remember, which is kind of like the percent in there. That's sort of where all this goes and what happens with it. Okay, and so just a couple of things then on terms of how these relationships can change. There's, if this is indeed normalized, and you can get a couple things like this, like if you look at all of the occurrences of all possible data points, and my infinity just kind of messed up there, of all possible data points. Again, if you interpret this as we discussed up here, the chance of x and x plus dx occurring, all that's going to be normalized to be 1. So that's nice about the limiting distributions. And likewise, the way we said the average is something like this big sum here of the frequency of occurrence times x sub I. Well, now in the continuous case here, the sum here is going to be replaced by an integral, as it always is. Now you be a little bit careful here. What is x sub I? Well, that's just x. And what is the frequency of occurrence? Well, this frequency of occurrence thing looks like it's become f of x times dx. Remember that little rectangular area that I referred to up here. That rectangular area, it was like I lost my pencil, right? That rectangular area as it occurred up there. But if I rearrange this a tad bit, we can make it look more like an integral to say something like x times f of x dx. This is sort of what my average would become. So now we can compute averages and that sort of thing. And there's analogs for the standard deviation and other things like that for this. But this business that I'm just trying to get you here, hopefully you can see then how you can make that transformation from discrete data And discrete data, of course, happens when n is something like really small. You can only do so much with that, to the case here where n becomes very large. You get a nice limiting distribution, so you can start using some calculus and things like that to understand your data. But it all comes from that histogram and getting more and more data and maybe pushing your data into the direction of a limiting distribution.